Okay. So the organizers kindly asked me to explain a few things about dendroidal sets, which I'm happy to do. So we've planned 2 slots of 2 hours this week and next. We'll have to see how it goes, but probably would be wise to take a little break after an hour. 2 minutes. Yes. So my plan is to explain the category of dendroidal sets, which is an extension of that of simplicial sets today. And an important feature of it is that it has a nice monoidal structure, a tensor product, which extends the Cartesian product on simplicial sets, but is not the Cartesian product. And then probably next week we will discuss the homotopy of theory of dendroidal sets in some detail. And so I can try to explain a little bit how these dendroidal sets model infinity-operads. And if we are very efficient with the time, then I can maybe talk a little bit about how it compares to other theories of infinity-operads, such as Lurie's or an approach via algebraic theories. Okay, so the most efficient way to start is to immediately change the meaning of the word operad. I'm sorry about this. So from now on, operad means colored operad. So I will explain what these are to those of you who are not familiar with it. And sometimes to emphasize the difference, if I want to speak about ordinary operads, uncolored operads, I will say things like classical operad, ordinary operad, or if I want to be a bit pedantic, monochromatic operads or something like this. Okay. Sorry? Co-operad, maybe. Copperad? No. Copperad with double P? Okay. So, a colored operad is a pair CP, but I will usually just write P, where C is a set of colors, and instead of the sequence of operations P of n, we now have operations which take n inputs of certain colors, prescribed colors, and spit out an output of another color. So, and for each sequence, C1, Cn, C, a set, simplicial set, space, chain complex, P of C1, Cn, C of operations to be thought of as the operations taking n inputs of type C1 types C1 up to Cn to an output of type C. Okay? And there can be constants in the theory, so to speak, so n could be 0. So you could prescribe some, in your algebras, you could prescribe some elements of a specific type. So speaking of which, let me say what, so in algebra, so there are conditions, there are the axioms just like for ordinary operads, but you have to modify the language a little bit. So for associativity, symmetry, and units. So now there is a unit 1c in P of C for every C. Okay? And the algebras, a P algebra, is a sequence A, C, C, and C, on which P acts by maps P, C1, Cn, C equals AC1, ACn to AC, satisfying the usual conditions. So these colored operads are good for describing structures which consist of more objects. So I missed the lecture last week, but we've been talking about operads and how they describe algebras of various kinds, associative algebras, commutative algebras, Lie algebras, and so on. If you want to describe, for example, a pair of a ring and a module, where the ring is not fixed but varies, you need a colored operad with two colors. Yeah? Many examples. For us, it's particularly relevant that you could have an operad where there are operations only for n equals 1. Okay, so a category with C a set of objects is the same thing as a colored operad. P, CP with P, C1, Cn, C, non-empty only if n is 1. Okay, so categories sit inside, I've drawn this described before, categories sit inside colored operads. And if you restrict yourself to the one object case or the one color case, here you get monoids, and here you get these monochromatic operads. It's a bit too long. One-ray operads. Okay, these colored operads, they form a category. So the maps are just like the maps between operads, but I would like to emphasize that I'm allowing myself to change colors. Okay, so a map between colored operads, let's say CP to DQ, is a pair alpha F, where alpha is a map between the colors, and for any sequence of colors, did I say C? Yes. Cn C goes from P C1, Cn C to Q FC1, no, alpha C1. Alpha C. Okay, so in the special case of categories, these are just the functors satisfying the obvious conditions, respecting the structure. So the structure is composition, symmetries, and units. Excuse me?
That letter next to the arrow, is it a Q?
It doesn't really matter as long as it's the same letter as this one. But it's a Q. It's my Q. Sorry about this. Okay. So I would like to describe for you a small subcategory of the category of colored operads, which in some sense generates these colored operads, just like the category delta of finite linear orders generates the category of categories. So we'll describe a full subcategory omega contained in operads, i.e. colored operads, parallel to delta containing categories. And the objects of omega are trees. And they're the same kind of trees as the ones I drew for you 2 weeks ago. You look a bit worried, so you don't remember.
You say that your opera form a category, but do they form a two category? Like the
Yes,
category?
yeah, there is some sort of notion of multi-natural transformation. But I will not talk about that. So there are trees, and they are, this means finite rooted trees with leaves, possibly with leaves, and just to warn you, again, they need not be planar. So don't be misled by the pictures I'm drawing, because when I draw a tree, I automatically equip it with a planar structure. So the trees look a little like this. For example. So this is the root. I could label the edges, A, B, C, D, E, F, going around the tree in the planar structure that I got from the drawing. This is the root, and these are the leaves, 3 leaves. Okay? Root always at the bottom. So any such object generates a colored operad. Any such tree generates a colored operad, which I will denote omega of t, and its colors are the edges, and its operations are generated by the vertices. Okay, so this may be, if you haven't seen it before, many of you have heard me talk about this before, but if you haven't, let me be a bit more specific. Let me name the vertices V, maybe U, V, W. So, in the example, there are operations. So let's list them. U in omega t of B, C, A, V in omega t of D, E, F, C, and W in omega t of nothing, and it spits out something of D. Okay? I'm just copying what is in the picture. U goes from BC to A, V goes from D, E, F to C, W goes from nothing to D.
So the middle one is DF, semicolon C, isn't it?
Yes.
So I think that
Okay. So, and other generated operations, among the generated operations, you could apply a symmetry, so you could have U times tau, for example, in omega t of CB A. You have to insert the units, so let's say 1C, doesn't matter, omega t C C, and you could compose, so you could have U circle over the color C V in omega t. And now I have to step back a little. U compose with V, so that should go B D E F, B D E F into A. Okay?
So are your edge labels necessarily distinct?
No, but the set of colors is the set of
That's fixed.
edges. So distinct edges are distinct colors, and it's easy to talk about them if I give them names, but that's all. Yeah. Perhaps what you had in mind is that between any given an n tuple of colors and another output color, there's at most one operation between them. Yeah? So in some sense, the edge is in some sense it's a partial order rather than a category, except that there are multiple inputs. There's one thing I should emphasize. Earlier I said U is a generator from BC to A, but the tree is not planar, so I could have drawn the tree like this. Yeah? So that changes the generators, but not the operad. Okay? So that's important to keep in mind. So the planar structure, a planar structure, corresponds to a choice of generators for omega t, but the generated operad doesn't depend on it. Okay. For one thing, this construction is well, no, let me leave it at this.
But your circles are not always well defined. So for instance, here I cannot do U circle 1 with anything. I mean, if I want to do U circle 1 W, it's not defined.
No.
No.
There's a composition. So I didn't say that in the beginning, but
Yeah.
so maybe I should have. If you talk about the substitution in a colored operad, it's like composition in a category. You can only substitute if the colors match. So for this input color C1 up to Cn, you can substitute operations, but they have to have output colors C1 up to Cn.
So is it really obvious, this statement you put in the box there?
Yes.
It is?
Yes.
Okay. I'm just checking out following.
At least given the time I have, it is.
So, but in the tree, the label of the edges are always distinct.
Yes.
Could imagine that you could repeat it, but you don't.
So let's look a little bit at this category omega, because I could have given the definition in a slightly different way. I thought about this one. Walking here, what would be perhaps the quickest, because you can give some sort of combinatorial definition without talking about colored operads, but purely in terms of trees. Okay, so some maps in omega. I didn't say what the maps are. Sorry.
You did.
Did I?
Because
Oh yes, it's a full subcategory. Thank you. Yes. So I can some maps. Thank you. So let me draw the same picture. A, B, C, D, E, F, V, U, G, W, A, B, C, D, E, F. Okay. So we have this operation U circle C, V. So there will be a map like this, B, D, E, F, A, X. I hope I did it correctly. These labels don't mean anything. It just indicates what the map is on colors. Okay? This edge goes to this edge goes to this edge, and so on. And this X is a generator, and it's going to be sent to the operation which is not a generator, but which is the composition U circle V. Okay? X goes to U circle C V. And if you read it graph theoretically in the other way, this corresponds to contracting the edge C. So I denote this arrow, I denote it by delta C. And I call it an inner face. Okay, I could also chop off, for example, this vertex W. So there will be an arrow like this, which I call delta W. And if you think that's special because W is nullary, there is a further one like this, which would be delta V, U, V, U. These are external faces. They just embed a smaller operator into a bigger one. Yeah. External faces. You could also, you see, this root vertex is a bit special because if you throw it out, there's really only one tree above it. So you could cut the tree like this. That's also an external face. So maybe for emphasis I will write it here. So that will be delta U. It's a bit special because it's a root face. It cuts off the root. And you cannot cut off the root if the tree would look like this, because you wouldn't know which part to keep. Okay? Am I clear? Am I going too fast?
Sorry, could you label the tree in the middle?
This one?
Of external faces, I'm a bit confused.
This one?
Because it looks the same.
You just have edges. You remove the vertex
Oh,
W.
you remove the
You remove
vertex.
vertex W.
I see.
So remove W, but
That's why it's called delta W.
Yes.
but there are still 3 leaves.
Yes.
Are they meant to be 3 or 2?
No, they're meant to be 3.
Makes the
And what-
You've lost a leg. It's lost a dot.
But he
It's completely analogous to the one which would have looked like this. No?
Okay.
Is that the morphism of operads? Because in the morphism of operad, the arity is fixed.
Right?
Yeah.
The arity is fixed. I will come back to this.
Maybe that's why it's confused.
That's
I
why
am
I'm
too.
confused. So, is there an incoming colour D? I don't think there is.
There is a D here. D, E, F.
Okay.
These edges are going to be set to these edges. This V, this thing which I call V, is going to this thing which I call V to
Oh, I
indicate.
see. Sorry, yeah. It's a map of operads, not a map of elements of operads. Yes.
Well, a map of operads has to send colors to colors.
I'm happy now.
Okay? This determines the effect on operations were there to be a map of operads. Not every function of colors will define a map between the operads. Okay? And as Bruno just pointed out, it has to preserve arities as well. Okay? Good. So let me draw another one. A, B, C, C prime, U, V, W, D, E, F, Y. Here you have two distinct colors, generated colors, C and C prime, and a unary operation from C prime to C. You could decide to send C and C prime to the same color C, and Y to the unit, yeah? To the identity. The identity is not a vertex here. So I never said vertices should go to vertices. Yeah? Vertices can go to composition of vertices, composition of 2, or composition of 0. Okay. So this, I call it degeneracy, and maybe I call it, I don't know. This is maybe the degeneracy for C, or the degeneracy for Y. I don't think I'm very systematic about this. Yeah? Degeneracy. And then there are lots of automorphisms. So maybe I choose a very small example here. So what are these things? A, B, C. There will be a map here. U primed, C, B, A. And here will be an isomorphism sending U prime to U times tau, okay? And C to C and B to B. So that's an isomorphism of trees. So if you think about it a little bit, then every map in omega decomposes as first a composition of degeneracies, then an isomorphism, and then a composition of faces. And you probably know such a fact for simplicial sets, except that there are no isomorphisms. Okay? And these isomorphisms, I don't know to what extent I will get to that, but these isomorphisms are going to cause me a lot of trouble. Because as soon as I start doing homotopy theory, I have to do equivariant homotopy theory instead of ordinary homotopy theory. So you also know from simplicial sets, if you look at the book on simplicial sets from the 60s, they will put the degeneracies in a specific order and the faces in a specific order. I could have done that after I'd fixed the planar structure, but this on each of the trees, but that's not so important. So omega could have been defined like this. Making explicit the relations for composing these generating maps, faces, degeneracies, isos. Okay, you can write down the equations for the composition of two faces, for example. Yes?
So in this statement here about every morphism decomposes as, you're making no distinction there between the internal faces and the external faces.
No. I could also put these in a certain order,
Yeah.
but I would need a few minutes to think about this again. Yeah.
But I mean, there is a statement which says degeneracies, isomorphisms, internal faces, external faces. faces in some.
Probably first external faces, yes. Yeah.
Nice.
And if you take trees with one input, that is ladders, you recover delta.
Yeah, so you're anticipating my next sentence. Well, reminding me of what my next sentence should be. So there is an embedding delta to omega, and it sends n to the linear order, the tree, which looks like this, with n edges. Yeah? So be careful. N plus 1 edges, yes. I number the edges 0 up to n, and the vertices are like the arrows. So this is a little different from the picture you would normally draw, because you would be inclined to write it like this, right? 0, 1, sort of dual graph. But this is because the arrows are like operations, and operations are like vertices. Okay. Now, if you, from this point of view, this is a full subcategory, and the names faces and degeneracies are exactly like in delta. And inner faces, outer faces, or external faces are exactly the same as for delta. But in delta, there are no automorphisms. Every automorphism is the identity. Yeah? It's a completely rigid category. We discussed the fact that a map between operads should preserve arities. So note, if S to T is a map in omega, and T is linear, well, T is linear is a bit ambiguous, right? Because this is also linear. So I should maybe say in the image of I. Then so is S. Yeah. Because in T there are only unary operations. So for every vertex in S, there's only, you can compose unary operations, but they will remain unary. So there are only unary operations to go to, so the operations have to be unary themselves. So S can have only unary operations, since T does. Maybe I'll write that. Because S can only have unary operations. T does. Okay? And there is another way of saying exactly the same thing. So for the tree, in other words, for the tree, this tree, which is I of 0, we have that if we look at the slice, omega over this tree is the same as delta. So omega will serve as some sort of index category for diagrams of sets or spaces, just like delta acts like an index category for simplicial sets or simplicial spaces. So I'll begin by discussing the sets. So definition, the category D set of dendroidal sets is the category of set-valued pre-sheaves on omega. So in symbols, D set is sets with omega op. Or if you're a Frenchman, are there any Frenchmen in the room? Well, Frenchmen of a certain kind. So, because of this functor I, so note the inclusion I from delta omega induces functors from simplicial sets to dendroidal sets and back. So simplicial sets is sets to the delta op. So here we have I shriek, and here we have I upper star. By Ken extension. So if you're unfamiliar with this sort of thing, it's completely determined by the following two, i.e. I shriek is left adjoint to I upper star, and I shriek is I on representables. And I will talk a lot about representables, so maybe also a bit of notation. So I think one of the usual notations is delta n for the representable simplicial set. So that's the simplicial n simplex. And analogously, I will write omega square brackets of t for the representable dendroidal set. Okay. But later I will just denote it by t. But I'll warn you when we get to that. So t is a tree or an object of omega. Omega round brackets of t is an operad, and omega square brackets of t is a dendroidal set. Okay, and what I just said could also be written like I shriek of a representable is omega of I of n, which is not very nice because of the double bracketing, but again, I've thought that before. So in topology, one often plays the game of exchanging categories for simplicial sets or their geometric realizations, spaces, or vice versa. And this is especially useful if you go to simplicial categories or simplicial spaces. And you can play exactly the same game here. So, and the starting point of this is the following square. So there is a commutative square so I will write this one functor again. Well, I don't know. Okay, maybe I should have written the other one. Okay, so simplicial sets sits as a full subcategory in dendroidal sets. I should have said something else about this. I'm getting ahead of myself. And categories sits inside colored operads because categories are the same as colored operads with unary operations only. Okay, so J shriek, view a category as an operad with unary operations only. And nerve is the nerve. And it's defined for categories and operads in completely the same way. So on the left, we have n of c of n is hom inside categories of n and c, where you view the partially ordered set n as a category, and n of an operad, Cp, which I will always just write n of p, now is a family of sets indexed by trees. So I have to specify its value for a tree. Yeah? And I will write hom in operads of omega of this with the round brackets, omega of t p. So another slogan that you should try to keep in mind is that dendroidal sets are what you need to take nerves of operads exactly like simplicial sets can take nerves of categories. Yeah? Right, dendroidal sets are a convenient category. I would like to write out the category, but that might be a bit. Let me be more modest. Convenient category for taking nerves of operads. I'm losing my voice. Okay.
Is there a J here? You've got a J lower shriek.
This is a J lower shriek.
Yeah, but is there a J without a shriek?
Uh,
I mean, because I comes from the embedding of delta into omega, right?
I don't know. No,
Okay. No, I just.
It's a philosophical question, perhaps. Anyway, J shriek does have a right to join, J upper star.
Okay, I suppose that's the answer I was after.
And you can, these nerve functors have left adjoints, which are sometimes denoted by tau. So for a simplicial set, from a simplicial set, you can generate a category whose objects are the vertices, whose arrows are generated by the one simplices, and whose two simplices give you commutative diagrams, commutative triangles. And I also had this. Yeah, that's all. So the diagram of left adjoins commutes, the diagram of right adjoins commutes, but also the right adjoins here and the left adjoins here commute. I will always try to write the left adjoins on top and on the left. So that's a convention which I learned from the papers of Quillen, and it's quite handy. And there was another thing I should have mentioned before. So, remark, the identification omega over I of 0 equals delta gives an identification dendroidal sets over eta equals simplicial sets, where I will use this object a lot. So eta is I shriek of delta of 0 is omega of this tree, under which I shriek corresponds to the forgetful functor. Okay. If you have a dendroidal set with a map to eta, that's the same thing as a simplicial set, and if you want to make a dendroidal set out of it via I shriek, it comes down to just forgetting the map to eta. So for the toposophers among you, so eta is a subobject of the terminal object, so the map to eta is always unique. This was also already implicit in what I said before. And so simplicial sets becomes an open subtopos of dendroidal sets. Yeah? If you think of these things as spaces, simplicial sets is an open subspace of dendroidal sets.
What do you mean by just over eta?
Comma category. You have another notation? Comma category. So, yeah. Localisation of objects. X to eta. So this equation will keep on coming back, because anything I will do for dendroidal sets will immediately have implications for simplicial sets, and vice versa. Anything that you know for simplicial sets or simplicial spaces, you try to generalize, to lift, to extend to dendroidal sets or dendroidal spaces. So that's part of the game that I'm going to play. So, I will define dendroidal inner CAM complexes. Then, when we've done that, might be a good moment to take a break. So I need to build up to it a little bit. So consider first for a representable dendroidal set omega of t, its boundary delta omega of t. Okay, that's no longer representable. It is the union of the images of the faces exactly as for simplicial sets. Yeah? Let's look maybe at an example. So if you have this tree, U, V, and E for the edge, it has three faces. So this would be delta U. I chop off the root. I could chop off the top. This is the same T. Okay. Or I could contract the edge E. Okay.
So in the faces you can either contract an edge or a vertex.
You can either contract an edge, and if you contract an edge, the arrow goes from the contracted tree to the bigger tree, or you can chop off a vertex.
Okay.
Yeah. And it's the same for this. In the simplicial picture, you see 0, 1, 2, 3, let's say. So this would be delta 3. You could, if you think of delta I, you think of leaving out the number I, okay? But the number I is now an edge. And if you leave out the number, a number in the middle, you should think of this as contracting the edge, okay? And if you leave out a number on the outside, you should think of it as chopping off. So you have delta 0 here. Okay, which chops off 0, and you also have 0, 2, 3, delta 1, which contracts 1. Of course, this also, these names don't mean anything, right? So it's the same. So I'm really not doing anything other than what I would do in simplicial sets. And in defining these boundaries, you don't see the difficulties of the isomorphisms because I'm taking images. So I work over the category over T, as it were. And the boundary is invariant under automorphisms of T. Okay, so once we have the boundary, I could also take the union, not of all the faces, but of all the faces except one inner face. Okay, for an inner face in T, right. So again, I'm copying a suggestive notation from simplicial sets. For the union of all the faces of T except the one given by contracting E. Given by contracting E. A more positive way of saying it would be, and this is okay, a more positive way of saying it would be the union of all the faces that contain the edge E. That's sometimes a little easier to keep in mind.
You mean inner edge, you say inner.
As of all the
You say for an inner.
all the faces except the one, the face
No, you said for an inner.
edge. I'm sorry, very good, yes, thank you. Thank you. So definition. Now maybe let's look at the example. So in this very simple example, the horn, this horn here, is the union of these two faces. You don't have this one. Okay. So definition. The dendroidal set is called an inner Ken complex, dendroidal inner Ken complex, or an infinity-operad if given any tree T and any inner edge in T and any map. Did I give the name? No. X. So for any inner edge E in any tree T, any map, let's give it a name, F, extends to a G. Okay, not necessarily uniquely, of course, just like for ordinary Ken complexes. So my claim is that these infinity-operads, which are very simple combinatorial things, form a very good model for the homotopy theory of topological colored operads. Yeah? And I can make this precise in terms of various equivalences of Quiller model categories, for example. So these inner Ken complexes are the vibrant objects in a model category. And if you slice this model category over eta, you find precisely the Joyal-Lurie model category for infinity categories and so on. So that's a little preview of where we go after the break or next week. So maybe I suggest we stop for 10 minutes or so.